Welcome back to che531. In this video, I'll be talking about linear programming. By definition, linear programming is problem of optimizing a function subject to some constraints. So the function that we want to optimize is called objective function, and the constraints are just the constraints. So for example, if you want to optimize sum of x1 plus x2, okay, in other words, if we, or maybe specifically, we want to maximize x1 plus x2, then this one is called objective function. And the constraints that we have, let's say, are these three, and these are called constraints. Okay, so one is x1 plus 2x2 less than 4, 4x1 plus 2x2 less than 12, and minus x1 plus x2 less than 1. So these are the three constraints we have with the two unknowns, x1 and x2. Also, the non-negativity properties of x1 and x2 are implied. So in all optimization that we look at in this course, considers x1 and x2 to be, or any variables that are used in the optimization, we assume that all of them are non-negative. Okay, so even if you don't write them, these are implied. Okay. All right. Now, since we defined the objective function and the constraints, we're going to look at a simple problem in two-dimensional space. Okay. So let's say the problem just talked about it up here. Can be shown in a 2D plane of x1 and x2, okay? Because I have two variables, I can do that. But if I have like 3 or 4 or more variables, it would be very difficult to show it on 2 or 3D plane, or 3D space, actually. Okay, so if I stick the 2D plane of x1 and x2, I can easily go and plot these inequalities on this 2D plane. To plot an equality, the way we do this is we convert the inequalities to equalities, and then we look at which side of the line, well, these are basically just lines, and we're going to look at which side of the line satisfies these constraints. For example, if I want to draw this constraint on a 2D plane, I change this less than symbol to equality, or basically I change the inequality to equality. Then I'm going to go and plot x1 plus x plus 2x2 equals 4, which is going to be this line. And then I have to decide the bottom side or the top side of this satisfies this constraint with inequality. And the easiest way is you just test one point, especially 0, 0, or the origin is the easiest, I think. So we're going to plug origin into the equation. If the origin satisfies this inequality, that means the bottom side of this line, the whole bottom side of this line will satisfy this constraint, because the whole bottom side includes the origin, and if origin satisfies the inequality, everything on the bottom side will satisfy the equality. If the origin, on the other hand, does not satisfy the inequality, then everything on the bottom side of this line will not satisfy the inequality. Okay, so just we use origin as the test point. Now, let's go ahead and plug the origin in here. So 0 plus 2 times 0, so the left side is 0. And of course, 0 is less than 4. So 0 satisfies this inequality, meaning that the bottom side of this line satisfies this inequality. So far I realized that the bottom side, the whole bottom side actually satisfies this inequality. With the same way I can go and find the region in a 2D space that satisfies this inequality, the second one. So this is the line for the second constraint. And if you test 0, 0, you see that 0, 0 satisfies this inequality, meaning that the left side of this line satisfies the inequality. Okay. And we go ahead and do the same thing with the third inequality, and we see that that line is going to be this. 0, 0 satisfies this inequality, which means the bottom side of this line, satisfies the inequality. So overall, if I get the common area of all of these, you would see that this polygon is the region that satisfies all inequalities. That's the common area, right? The left side of this, the bottom side of this, and the bottom side of that will lead to basically this polygonal shape. Now, I also bound this actually polygon by the x2 and x1 axes as well. Why? Because we know that the variables are non-negative. And because of these, we actually have two more constraints, this one and that one. And you can easily see, the top side of x1 and the right side of x2 are basically the regions that satisfy these two inequalities. So overall, if I put all these 5 inequalities together, it's going to be this polygon. So back to the problem, I want to maximize sum of x1 plus x2, and I know that x1 and x2 should be somewhere within this polygon or on the border. Okay? So from this point on, we're going to accept the first theorem in linear programming. By the way, linear programming is called linear because we are assuming that every function in here, the objective function and all of the constraints, are linear. Linear means you do not have like multiplication of two variables like x1 times x2, or we don't have x1 raised to the second power, or we don't have x2 raised to the second power. Everything has to be first power, and we do not have multiplication of variables. So that is what we mean by linear. Now, the programming word of this topic actually is coming from, you need a little bit of, I think, programming to be able to optimize the problem. So in the realm of LP, which means linear programming, everything has to be linear. All right. Now, with that, we're going to look at the first theorem. The first theorem in linear programming indicates that the solution is, or the solution that optimizes the objective function, either minimize or maximize, is one of the corners of this polygon. That means the solution is not going to be inside, it has to be on the border. Also, not only the border, but also the corners of the borders. So if you accept this theorem, all we need to do is just we go and test the corners. And we find the one that actually maximizes our function. Okay? So the method that actually goes and finds the corners only is called Simplex Method. So we're going to look at that in a minute. So that is actually on page so it starts from page maybe 71, the bottom of 71. So we're going to look at this, how Simplex Method solves this problem. So again, we know that the solution is on the border because of the theorem of linear programming. And now we're going to use Simplex Method to just define or determine the corners. Okay, let's go back to the problem. This time actually I have a better, or maybe a rather simplified problem. Instead of 3 constraints, or 5 constraints, I'm going to have 4 constraints just to simplify the problem, not really to skip that problem. This is basically for simplification of the explanation. I have 2 constraints. 2 constraints are also implied, so overall 4 constraints, and objective function to maximize. Okay, so the first step is we're going to convert all of the inequalities to equalities by adding new variables called slack variables. For every inequality, we're going to have a new variable or slack variable, and then by introducing the new variables, we're going to replace the inequalities by equalities. For instance, if I have 2x1 plus x2 less than 4, I introduce a new variable like x3, and then I change this less than or equal to. I'm going to change it to just equal to. So it's going to be like that. 2x1 plus x2 plus the slack variable x3 is equal to 4. Similarly, I convert this inequality by adding new slack variable, or x4, to equality. That becomes x1 plus 2x2 plus x4 equals 3. Alright? So this is the second step. Third step, I'm going to convert my objective function to equality as well. How can I do this? Well, I'm trying to maximize x1 plus x2. I'm going to just say, what if I just rename x1 plus x2 as just another variable z? Okay, so so far nothing has changed. I just lumped the x1 and x2 into just one variable z. Now I'm going to move these two variables to the left side, and now I'm going to have z minus x1 minus x2 equal to 0. Okay, so I converted my objective function to some sort of equalities again. Okay, so now I have a bunch of equalities. I can put them into a matrix form like the following. The first line of this matrix is just the objective function. Okay, z minus x1 minus x2 equal to 0. I just put the coefficients down in this line. So the coefficient for z is 1. The coefficient for x1 is minus 1. The coefficient for x2 is minus 1. There is no x3 here, there's no x4. So that's why the coefficients for those are 0. And the right-hand side is also 0. So that's the right-hand side. So I'm done with the objective function. I'm going to do the same thing for the other two constraints. The first one, what is the coefficient for z in here? And so there's no z there. That's why the coefficient is 0. What is the coefficient for x1? And that is 2. So here's 2. Coefficient for x2 is 1. Here's 1. Coefficient for x3, here is 1. There's no x4 here. That's the coefficient. That's why the coefficient of x4 is 0. And the right-hand side is 4. Similarly, I can put down the coefficients for the second constraints as 0, the coefficient for z, because there's no z here. 1, 2, 0. 1 is the coefficient of x1. 2 is the coefficient of x2. There is no x3, so that's why I have 0 here. And then the coefficient for x4 is 1. The right-hand side is 3. So now I'm going to have 3 rows. Let's say row 0, row 1, row 2. Row 0 is the objective function. All other rows are the constraints. Okay. So far, I converted the objective function and the inequalities to some sort of equalities. Okay? All right. So here's maybe a step 3. So step 3 says the first corner of that polygon is defined by setting the non-basic variables to 0. But what is non-basic or basic variables? The variables that we introduced, the slack variables, are called basic variables. Okay? The other variables like x1 and x2, not z. Z is basically in what we call it the objective function, so we do not talk about z for now. Other than x3 and x4, which are basic variables or slack variables, other than these two variables, the other variables are called non-basic ones. In this case, non-basic ones are x1 and x2. So I'm going to go ahead. Well, actually, I have a better definition of basic variables here. So basic variables or basic variable is a variable that only shows up in one equation. And those are pretty much like slack variables like x3 and x4. So these are basic ones. And everything other than these will be non-basic, which is x1 and x2. Okay, the first corner of that polygon is defined by setting the non-basic variables to 0. Okay, so I'm going to set the non-basic variables to 0. So stay tuned for the next part of the video in linear programming.